Hello everyone, we will continue with our last lecture today, and before end of this course I thought an appropriate topic is some review of Kalman filter theory, because without that probably in my view no control theory is complete. So, obviously, I will not be able to do a justice with all the derivations and everything about Kalman filter theory, but I will be able to give you some sort of a summary or a little bit theory around that, so that you can actually take this and implement in your problems actually. So, let us do that, but before doing that let us go through a little bit on what we discussed last time, okay, and that was about this LQ observer that we discussed last time actually. So, a very quick review of that. So, this is what we did there, observers and all we are need, because this, I mean the need for the observer or estimator is because we typically propose state feedback control design, and state information is needed for control computation, and most of the time we may not have sensor rich systems. In other words, either the sensor is not available, expensive sensor, all that actually whatever we discussed last class. So, what we do here in an observer for linear system design, we have a system plant like that. We propose that a observer dynamics be constructed like this, where k is an estimator gain, and then we discussed about the error being x minus x hat. Hat is the estimated information, x is the true information. Then what happens is like you go through this error dynamics and things like that, and try to make sure that it is not a function of the error dynamics is, I mean the x tilde dot is not a function of state and control. So, we enforce these coefficients to be 0, and then we derive this estimator dynamics, observer dynamics to be of this form. So, it exactly falls into this form, that x plus bu, but we have an additional term ke, that is estimator gain times y, that the actual output minus estimated output C x hat actually. So, that is the innovation term. So, you have that filter dynamics as like a linear system dynamics plus a Kalman gain times innovation term actually. Then we went ahead and saw a comparison between control design and observer design, where it all okay, the closed loop dynamics of the for the control system design is like that, and closed loop error dynamics for the observer systems, I mean turns out to be very close to that actually. Then we discussed the objective here is like x should go to 0, and that is keeping that objective we have designed an LQR controller, and objective here is also x tilde should go to 0. So, fairly similar objectives. Only problem was k happens to be in the left hand side here, whereas it happens to be right hand side here. So, we took transpose of this matrix, and by doing the transpose k transpose turns out to be the right, and then we told okay, we can actually treat this A transpose and C transpose as equivalent A and B, and then design a KE transpose instead. Instead of directly designing KE, we will be able to design KE transpose, but once we design that, then taking transpose means we are done with the design actually. So, for that we have this system dynamic original system and had a dual system, and observe that controllability for one is observability for the other, and vice versa. So, if you see this closed loop system dynamics and all, so we propose that this KE transpose is should be designed as similar to what we design as Kalman gain actually, I mean for this for the control design part of it, LQR gain. So, instead of R inverse B transpose P, we should have R inverse C times P, okay, and this P should be like a solution of this matrix and things like that actually. So, anyway, we continued with that, and then the observer dynamics turns out to be like this with the way to design and observer gain actually. So, this all turns out to be like the LQ observer design, and then we will see, I mean we have also told towards end of the last lecture is like if you consider the system dynamics with the noise, process noise and sensor noise, then it also turns out that the filter dynamics and all remain similar, and then that is the little bit more detail we will see this in this class and continue further actually. So, this is about this lecture is about Kalman filter theory. So, we will revisit that towards the end of the lecture what we discussed last time, and then continue further actually. So, outline of this particular lecture will be something like this. We have continuous time Kalman filter that we touched upon in last class. Then we will extend that to discrete time Kalman filter. So, the system dynamics is given in discrete form now, and the measurement is also given in discrete time. Okay. Then we will try to combine the two and tell okay, how about a continuous discrete Kalman filter. In other words, the system dynamics is continuous, but measurement comes at discrete time. So, that is what reality is actually most of the time. And this will give us a platform to talk about something called extended Kalman filter, which is used heavily in practice. And most of the time when people tell I have kind of used a Kalman filter, that is what they mean. They mean they have actually implemented an EKF into their design basically. So, up to that we will discuss in this lecture, and then probably that will be a good summary before we wind up this course. Alright, so continuous time Kalman filter design for linear time invariant system, that is the basic starting point, and that is what we discussed last class also. So, we have a system dynamics which is like x dot is Ax plus Bu plus Gw, okay, and then measurement equation turns out to be y equal to Cx plus V, where W and V are like W is process noise vector and V is sensor noise vector. Okay. And remember these are affecting the system anyway, because the W is nothing but an input which is directly affecting the system states. Okay. And if you really want to estimate a state into the feedback control design, that means U becomes an estimated function of an estimated state, then for the estimation process you will use Y, and Y is corrupted by sensor noise anyway. So, these two will affect the system dynamics, they will affect the performance of the controller like that actually. So, before we proceed further, here are some of the assumptions involved, and what it means is x initial condition of x is given like this, okay, W is given like this pair q 0 q and V is like 0 r. What it means in this parenthesis is the first thing is mean, the second thing is variance actually, or if it is a vector it is called covariance matrix. So, that means x of 0 initial condition mean value is x tilde 0, okay, and the covariance matrix is P naught. Similarly, Wt which is a process noise has 0 mean and Q as the covariance matrix for this. Okay. What is the covariance matrix by the way? This is all given here. Expected value of W times W transpose is actually Q if tau is equal to T, tau is 0. If tau is not 0, then it will happen to be 0 actually, because the delta function is defined like that anyway. So, this is Q means that expected value of W times W transpose at the same time basically. Okay. So, that is what it means. Anyway, so we also assume that this W and V are uncorrelated white noise. That is the fundamental backbone of Kalman filter theory, that this noise thing that are accounted for are assumed to be white. They may or may not be white, but in the entire theory development they are assumed to be white. And what you mean by white is like they are supposed to be like uncorrelated. That means, if I take the correlation process and all are defined like this. If I take any other time like t and t plus tau, where tau is a non-zero quantity, then I should get 0 actually. Okay. So, there is nothing, if I multiply the same process noise with the same point of time, then I will get q, but if any other time if I multiply, then I will get 0 actually. So, these are like what are called as white noise basically, and they are assumed to be 0 mean actually. W and V are assumed to be 0 mean. Okay. Alright. So, objective here, what is the problem statement? The objective here is to estimate the state vector x at t using the state dynamics as well as a sequence of measurement actually. So, we are not talking about only a single measurement, we have to have a sequence of measurement, and using all those sequence of measurement, if observability is there, that means if I keep on taking sequence of measurement and as a combination actually, those sequence of measurements will be affected by system state actually. Okay, that is the meaning of observability. Assuming that observability is there for the system output and system dynamics pair that we are talking about, then what we really talk is we take sequence of measurements, they are corrupted by noise alright, but still we will be able to get a good estimate x at of t. And what do you mean by good estimate? It again means that if I take x tilde, that is error between true and estimated value, that will become very small, and ideally x tilde should go to 0 as t tends to infinity, but in a stochastic sense where this noise vector is there and all, this will not happen in this manner, even though we would like to happen actually. So, what will happen then? The expected value of x tilde will go to 0. Okay. If I take expected value means it is a large is a average of a large number of cases actually. So, if I keep on taking this x tilde t for a large number of discrete point of time probably, then if I take the mean value of that, then that should go to 0 at least. Okay. So, the expected value sense it should go to 0, that is all we are demanding actually. Okay, so let me probably write it here. What we are telling here is expected value of x tilde t, okay, should go to 0. That's our objective actually, truly speaking. All right, so let's see that how does it happen. We'll get motivated by this LQ observer that we discussed last class and all, and take, okay, we'll assume the same observer dynamics rather. It's not similar, it's same actually. Okay. So, we will just take Ax hat plus Bu plus gain times estimated gain times y minus y hat, where y hat is the estimated output and estimated output will turn out to be Cx hat again actually. Okay. So, this derivation is fairly straightforward, because see y x hat by definition is expected value of x. Okay. What we mean by x hat here, okay, is not this x hat is nothing but expected value of okay. All right, let me all right. Okay, this x hat is nothing but expected value of x actually. Okay. So, in that sense, the y, if you continue with y hat, then y hat is expected value of y, and y is nothing but Cx plus v, and a great property of that expectation operation is it's a linear operator. So, you will be able to split it out and take C out of this operation. So, it turns out to be expected value of v is anyway 0, because it is a 0 mean white noise. So, this is because of that the expected value of v turns out to be 0, and expected value of x is x hat by definition. So, y hat turns out to be Cx hat, and that is how it will operate actually. Now, the problem is how do you come up with this design of Ke. So, this is what is required anyway. Without that, we will not be able to propagate the system dynamics actually. So, we will not go through the entire derivation. It will require probably a full class and all that. So, what I will tell is just a summary part of it, and summary part is like the gain what we are talking about here, Kalman gain can be computed like this: P C transpose R inverse. Okay. And then P C transpose R inverse, this what is that? After we compute this, then x hat dot is nothing but A x hat plus B u plus K times y minus C x hat actually. So, how do you compute this P? The P is given like you can solve this Riccati equation, it is called filter Riccati equation actually. And if you see this Riccati equation, if before what we discussed, the only difference is probably this term actually. Okay. So, this term the LQ observer sense, this term earlier it did not have a G in the left and G transpose in the right, actually only it was only Q. So, if you assume that G is actually like a identity matrix here, or G W is the noise, not W per se, then it is nothing but an LQ observer actually. In other words, LQ observer is also like a Kalman filter, where we are assuming that G is actually identity matrix. May not happen, of course. The W may not, W is like a control input may not alter the x dot directly, by the way. It passes through a influence matrix anyway, G, it is like a V matrix. Okay. So, if you assume that G is actually identity, then it is nothing but what a LQ observer actually. Okay. Anyway, so this is how it operates. So, if you really want to mechanize a Kalman filter like this, all that you have to do is initialize x at 0 with a guess. Okay. Then you have to solve this Riccati matrix P for the filter algebraic Riccati equation. Again, this is in the framework of infinite time. That means it may take a little longer time to stabilize actually. So, if your TF is infinity, then this is 0, otherwise it will not be actually 0. Anyway, assuming that it is this algebraic equation, Riccati equation is to be solved, which is called filter Riccati equation, and then this after you solve for P, you compute the Kalman gain something like this, and once you are there, then you can propagate the system dynamics, because you already have an initial condition there. And it will also lead to this good stability behavior and things like that. That means the error that we are talking about, x tilde, which is expected value of x tilde and all that what we discussed here, it is all guaranteed to happen actually, because it is a linear time invariant system. Okay. And there are also nice properties associated with that, in the sense of this is of something called separation principle and all. That means you can design a controller and of the estimator separately actually. So, it will not hurt the stability behavior of each of the thing, even though you want to operate it based on a feedback system. I mean, if you want to operate u based on a feedback of estimated state, then although nothing is going to happen drastically wrong basically, because the closed loop eigenvalues will be eigenvalues of this system, I mean, and the eigenvalues of the aerodynamics and all that. So, those theorems are there, I will not discuss too much on that actually. So, this is the summary of how do you mechanize a continuous time Kalman filter. But that is not the problem here. Is this entire formulation assumes a continuous availability of measurement. Y is X plus V, that means continuously the measurement is coming to us actually, and certainly that is not reality. Okay. Measurements are taken only at discrete point of time actually. So, if that is the case, then it also makes sense to probably discretize the system equation, system dynamic equation. I mean, we have several methods anyway. You can use zero order hold, Euler integration, all sort of things, I mean, whatever discretization method. So, once you discretize the system dynamics and the measurement is anyway coming in discrete manner, then probably we will have a compatible system to talk about actually. So, that is what this discrete time Kalman filter theory talks about. Okay. So, let us talk about that. Okay. So, what we are assuming here is a discrete time system model, again linear system, and when you talk about discrete time system, normally there is no difference whether you take like a time varying system or time invariant system. So, we will just take time varying system actually. So, x k plus 1 is a k x k plus b k u k plus g k times w k, y k is c k x k plus b k. So, remember a k, b k, c k, g k, all that they need not necessarily be constant, they can be also be time varying actually. Okay. Again we assume that w k and v k are 0 mean uncorrelated Gaussian white noises. These are like a little bit strong assumption, but then these are standard assumptions for Kalman filter theory. So, they are corrupted by noise, all right, but the noise satisfies this property. Both of the noise have 0 mean, they are uncorrelated, and they are Gaussian processes also. Okay. Gaussian makes it probably, the assumption of Gaussian is more, I mean, done to both address the realistic situation, that most of the time the noise happens to be Gaussian, and once you assume Gaussian noise, there are a lot of nice properties actually, for which the theory becomes complete. For example, if you have a Gaussian distribution, then mean and variance gives us the entire meaning. I mean, more than that there is nothing actually. So, if once you know the noise is actually Gaussian, and once you know the mean and its variance, then we are probably done actually. Okay. Theory becomes complete basically. But for the entire derivation, remember, I mean, in my view, all that is required is that it has 0 mean and uncorrelated things. So, 0 mean white noise, that is all we need actually for the derivation part. So, let us proceed with that. Then because of these assumptions, these hold good, and what it means is, if I take expected value of w times w transpose, if they are not taken at the same instant of time, that is 0, okay, nothing happens there. If they are taken at the same instant of time, then this q k matrix pops up, and this q k is called process noise covariance matrix actually. Similarly, if you take sensor noise covariance matrix, that is the relationship it needs to satisfy. So, if they are not taken at the same time, that is 0. If they are taken at the same time, then this is RK matrix. Okay. And if you take even at the same time, whatever time, same or different time between V and W, then it is 0. So, they are totally uncorrelated to each other actually. Okay. So, it is either autocorrelation sense or self correlation sense, that happens that way. But if you take cross correlation sense, V k and W k like two different things taken together on that, no matter whatever time you are talking about, they are all 0 actually. So, these are like, if you think, they are slightly strong assumptions rather, but there are also tricks and techniques to, if it is not really a white noise, how do you make use of it. There are ideas like shaping filter design, like you constitute some sort of a small system, subsystem rather, where you take white noise as input, and the output of that artificial subsystem should be really the color noise that we are talking about actually. Then you can augment the original system dynamics with that artificial system, which is like shaping filter design and all. Then you can talk about estimating the entire state vector actually. Okay. So, those if somebody is interested, they are encouraged to study details of those. Anyway, filtering theory is a fascinating subject. It is a complete theory by itself and all that actually. So, there are many tricks and techniques available on the way basically. Anyway, so coming back, this is what is assumed. Now, what is our I mean, what is the way to proceed further? So, we need some sort of a filter dynamics anyway. Okay. And the filter dynamics is an artificial system dynamics, which it simply needs to be propagated with some initial condition and some gain computation actually. So, there are two ways of doing this here in the discrete time setup. One is like I will assume it is a predictor corrector form, which is actually very popular. Okay. There are several reasons for that of course, and then there is a observer form, what you have seen in the this continuous time framework. So, observer form or recursive form can be derived from this, suppose I mean this from the predictor corrector form easily actually rather. Anyway, what you do here, first of all you predict, okay, for the next time step. Okay, let us talk about this. Let us assume that I know some state information already at kth instant of time, and I also know the controller at kth instant of time. So, I will be able to take advantage of this system dynamics without the noise of course, okay, and then I will be able to predict what is going on actually. Okay. That means, if the noise does not happen to be there, then I should have a better prediction here, whatever I will predict anyway. But remember, this prediction part does not assume any sensor information actually, and once the sensor information is there, that means sensor has given me some value, I will be able to update this value from that k plus 1 instant of time, and same thing happens at kth instant of time also. If I start with k minus 1, then I will get k actually here, and then k will be updated here. Okay. So, first prediction, then update, prediction, update, like that it will happen actually. Okay. Now, if you the reason it is written like here, not k plus 1 but k, is easy to see that if I substitute this expression here, then I will be able to derive this actually. So, this is observer form or recursive form actually. Okay. So, prediction correction form is more popular since it is more logical, structured way and easy to implement also actually. We will see that actually. It also leads to a logical extension in extended Kalman filter theory, which is primary requirement anyway. Before we proceed, a bunch of definitions. Remember, we are talking about plus minus all sort of things here. So, we will be able to do some of these actually. Anyway, so before we proceed further, this let me explain a little bit here. This okay. So, what you are telling here is something like we have this time sequence, okay, this is 1, this is 2, this is 3, like that. I will have this picture one more time later anyway. So, I start with some information here, and then I will be able to predict using the system dynamics that I know from step 1 to step 2. Okay, this is that time axis actually. Okay. Then when I have this measurement information coming, then I will update this here. Then I will again predict it here from 2 to 3, I will get some value, then I will be able to update using some sort of sensor information. Then I will continue that. So, this is the prediction part, and then there is a correction part actually involved. Okay. So, this is the correction, sorry, this is this way. Okay. So, predict, correct, like that it will happen actually. So, that's the meaning of that. All right. So, let us continue this. Okay. So, before proceeding further, let us talk about certain error values and all that. So, remember I have so the prediction part is written normally like minus, and the correction part is written as plus actually. So, when you see minus, that means it is actually coming from the prediction. When you see plus, it is actually corrected person taking the output information actually. Okay. So, prediction part and then correction part, like that. So, we assume, I mean, we will define this these error quantities, these error covariance matrices and things like that before proceeding further. So, this x tilde minus x tilde k minus is nothing but x k minus x k hat minus. Similarly, x tilde k plus is x k minus x hat k plus, and similarly k plus 1 and things like that. Now, error covariance matrix that we also need to define, I mean, we need to define it this way. P k minus, that is the error covariance matrix at time step k in the prediction part of it is given like this, expected value of x tilde k minus times x tilde k minus transpose, like that. They are all out of product anyway, because it, so each of that is n by 1 vector. So, if I get an outer product, it becomes like an n by n matrix basically. So, this error values error states are defined like that, and error covariance matrices are defined like that. These are simply definitions to begin with. And obviously, objective here is to derive expressions for these actually. We ultimately need to derive expressions for Kalman gain k e k, but also we need to derive these expressions p k plus 1 minus and p k plus, because k e k is a function of these. So, we need to derive expressions for that actually, and you cannot really start with the definitions, because these expected value means we should have I mean infinite number of these I mean values available to us, and then we have to take average value of that, and also from definition it will not be, I mean it is not advisable, it is not possible also. We need a kind of precise information like separate expressions to derive this actually. So, let us see whether we can do that. Now, expressions for p k plus 1 minus, okay. So, remember p k plus 1 minus is given like this. So, okay. So, we need to derive an expression for that one first, and then take the expected value of this outer product and all that. So, what is this? This is by definition is these two, okay. And then this x k plus 1 is like this, okay. Then this part is given like that from the definition. This is coming from this actually, okay. So, this part came from that, and then this part is nothing but the system dynamics, okay. Remember, estimated one is the no noise, but the true one is given with noise anyway, okay. So, now you see that these two are cancelled out, this v k u k will go from v k u k, and you are left out with only the rest of the terms, and that is given something like this, okay. So, if I see x tilde k plus 1 minus, it turns out to be like that. So, now I can take p k plus 1 minus, which is expected value of this times the transpose, and this one I just derived, this is like this. So, I will take a transpose of that also, then I will expand this transpose and then multiply, do the algebra and all that actually. And remember, these are all like cross correlation is 0. So, expected value of this w k and x tilde k, this is 0 and this is also 0. Yes, anywhere we see a cross correlation term, these are all 0 by assumption in Kalman filter theory. So, we take out those, and we are left out with this, and these values, remember whatever we have here, this is nothing but definition. If you go back to definition, this turns out to be like that, okay. So, this is nothing but p k plus actually, right. So, this one what you see here is nothing but p k plus. So, what you have here, a k times p k plus times a k transpose. So, it just comes from there. Many of these are simply like good bookkeeping basically. If you know what you are doing, substitute, expand, and then cancel out, put some see which all terms are 0 and deal with rest of the terms that are left out actually. Similarly, if you see this one, okay, expected value of w k times w k transpose, that happens to be q k by definition, and then it turns out to be like that actually, okay. So, if you really want p k plus 1 minus, then it is a function of p k plus and things like that actually, okay. So, this happens to be because this okay, w k and x k, these are all like what is called as orthogonal. Orthogonal means this expected value of that happens to be 0. Alright. So, this process will start from p 0 minus, and p 0 minus is like initial covariance matrix of this error vector and all that, and that is supposed to be selected by the designer basically. That is how you start with, along with your x 0 information, like a guess for the initial condition for the estimated state. You also start with a guess for your covariance matrix actually. Alright, so this expression is derived like that. What about the other one, that pk plus, because remember pk plus is required here, so we need that. So pk plus is by definition is expected value of xk, I mean x tilde k plus times x tilde k plus transpose. So we need to have x tilde k plus first. Okay, so this one is given like this by definition, and x tilde k plus is given by this. This is the predictor corrected form. So this expression comes there. Okay, so if you put this expression there, okay, this part here, and then try to simplify this, it turns out that okay, I can probably simplify that way actually. Okay. So I will combine this xk term is here, this xk term is here. So this is I minus k times ck, okay, times xk, and similarly I have this xk hat minus here and xk hat minus here. So I will put it there actually that way. So I will try to simplify this, and I got some sort of a formula like that. So pk plus is expected value of the same this expression times that. So I will put this one times that transpose, and then again do the same thing. I will expand this this bracketed term and then multiply and see what all simplification I can do. So it turns out that again this expected value of these are constant, they are like expected value is not a function of that. So I will be able to take out, and these are orthogonal to each other. So they will go. So what are left out? These two expressions, see this what I told here is these two expressions will not be required. So first and last will be there actually, and first and last by definition will turn out with this part, which by definition is pk minus, and this part by definition is rk anyway. So pk plus happens to be like this. Okay. So now we need to derive a kek like the estimator problem. So remember what is our problem actually. I mean the problem here is the pk plus, which by definition we will go back to pk plus is error times the error basically, the transpose of course, and this is after update. That means this if you see xk tilde plus, this is after this x at k plus. That means after I correct this using this innovation terms and all that, whatever I get is that, and then error term happens to be true minus that. Okay, so obviously if I take a kind of a covariance matrix for that, I want that to be minimum actually, as minimum as possible, ideally 0. So what I formulate a problem is, okay, let me go back and try to see whether I can minimize this operator, I mean this pk plus, and minimizing this pk plus means one of that is like a trace operator. Remember this is a pk plus is a matrix. So trace is nothing but a kind of a norm operator, okay, and the trace is like if you see that a little bit, that each individual terms will happen to be in diagonal, and trace is nothing but summation of diagonals actually. So if I just take this expression pk plus happens to be like this one, okay, and this if I take second norm square of this x tilde plus x tilde k plus second norm square, and that is nothing but trace of pk plus actually. Okay. So I want to minimize this expression half of trace of pk plus. So whatever happens, whatever the solution I will get is kek basically. So how do I do that? If I really want to minimize this j, the necessary condition is j. See, remember this j happens to be a function of kek. Pk plus there is a kek expression and all. Okay. So I consider this as a function of kek and then try to minimize that actually. So how do I do that? The necessary condition turns out to be like that, and j is this, where pk plus is this expression anyway. So I substitute that and then try to take this algebra, do this algebra. It turns out to be like this, and kek happens to be left hand side of both. So I will be able to take common out of that, and then I will solve for kek is like this. Okay. If I take right multiply with this inverse, this side you will get kek, this side will happen like that. So kek, which is Kalman gain in discrete time formulation, turns out to be like this actually. There is also an idea that okay, pk this is what we derived here. It seems slightly complicated. One does not have to live with that. You can actually simplify this expression. You can expand this thing and then cancel out a few terms, and it turns out to be as simple as that. But later we will see that this form is advisable because of numerical conditioning issues and all that. This is like a quadratic form what you see here. So the symmetricity of pk will not be compromised even because of numerical inaccuracies in computation and all that. So even though it is a slightly little more kind of computation, we still it is still advisable to use the bigger expression anyway. Okay. So, what is the summary? Summary is problem is like this. I have a discrete time formulation where xk plus 1 is like this, yk is like that, where w and wk and vk are uncorrelated, white noise, zero mean, orthogonal to state vector, all that is there. And then we start this process by initializing these two. We initialize the estimated value of the state as well as a guess value for the error covariance matrix. Then the gain computation can be done this way, where pk minus can be computed I mean using this propagation equation and all that actually. Okay. This is what you see here is nothing but propagation equation basically, what you see here. Okay. That means, if I know pk minus, I will be able to compute pk plus, provided I know kek basically. So, this is like, I mean, if I have an initial condition, I will be able to propagate this covariance matrix. Anyway, so this is what is going on here. So, we have a initialization which is done, then again gain can be computed like this, where and the update equations will proceed that way. So, this is after I get a measurement, I will update the state vector that way. Okay. So, it is my propagated thing, the prediction part of it plus the correction term which is coming from the measurement multiplied with a Kalman gain term actually. And then the error covariance matrix can be propagated this way or that way, but this is preferable anyway. So, we propagate that way and get ready for the next time step actually. Okay. So, after we are done with this, then we predict it again one more time step. Okay. So, both state as well as covariance matrix. So, this is because of this easy of implementation, is a logical flow of the expressions and all that, this discrete form is kind of very popular actually. The predictor corrector form is a natural way of implementation actually that way. Now, we will move further and then tell, okay, we seen continuous time Kalman filter, we have seen discrete time Kalman filter. Neither of that is actually a very good reality, because what happens is in pure continuous time Kalman filter, the assumption is the sensor noise, I mean sensor measurement is available in a continuous time manner, which is unrealistic. And in a pure discrete form, the system dynamics needs to be written in a discrete form, which is approximation to reality. Okay. So, I do not know, I mean given a choice, we will like to work with a continuous time state equation, but discrete time measurement equation, and that is where it will lead to continuous discrete Kalman filter. So, let us see that in brief. So, what you are talking here is the state equation is given in terms of continuous time. Still it is linear, but now let us talk about time varying system dynamics and all. Okay. And the measurement equation is given in terms of discrete time. You see Wt is a continuous process noise and Vk is a discrete sensor noise actually. So, they also satisfy the similar properties, and then remember one will satisfy in the chronicle delta sense, and other one is direct delta sense like that. This is direct delta, this is kind of chronicle delta basically. So, that means as long as t is not equal to tau, this is 0, if t equal to tau, this is 1, and similarly if k is not equal to j, then it is 0, and if k equal to j, this is 1, and that is that way. So, this is done because it is a discrete, I mean it is a continuous time formulation, and this is done because it is a discrete time formulation. Okay. So, probably this okay, there is a small mistake out there, k is not required for it. Okay. And this is what I was talking earlier, this is the discrete I mean this prediction correction mechanism is what is popular here. And so, assuming some value set t0, I will be able to predict it in a fairly continuous time manner, okay, using any numerical scheme, not necessarily zero order hold and things like that. You can just use any continuous time propagation expressions and all to predict this. So, once I predict it, then the sensor information is available, I will be able to correct it. I mean because the sensor will give me, assuming that that will give me correct information and all that, I will be able to take advantage of that and then tell, okay, I am already here, but let me not operate further on that, and let me correct myself a little there and then operate further. So, this is prediction, this is correction, again prediction, because in between I do not have any sensor information, I have to simply rely on what I have. So, starting with this initial condition, I will be able to predict, but at T2 I have got sensor information again. So, let me correct again from here. So, like that it will proceed actually. Okay. So, I mean in principle it is similar to what you have seen before. So, what it tells is propagate the state estimate model forward from Tk to Tk plus 1 using the initial condition and correct the information at whenever the measurement is available. That is what I told you before. Okay. So, what it turns out is that unlike this continuous time Kalman filter expressions and all, because the measurement is not available in between measurement is simply not there. It turns out that the covariance matrix, which is actually a continuous time expression this time, is given in a simplified form. That nonlinear term what we heard earlier is not there basically. Okay. So, this can be derived very rather easily actually. If you see this expression for P dot, this x dot is given like that, x hat is given like that. X hat dot is the prediction part, and remember that there is no noise in that actually. Okay. So, now if I see that the error definition and error dynamics and things like that, x tilde is x minus x hat. So, x tilde dot is x dot minus x hat dot. So, if I just take difference between the two, bu goes, and I am left out with a times x minus x hat, which is x tilde plus gw actually. So, I will be able to operate based on this x tilde dot is x tilde plus gw. So, remember this time varying system dynamics, and time varying system dynamics with W being the input matrix and things like that, I will be able to write the solution of that in a continuous time manner, where this phi t t 0 happens to be like a state transition matrix and things like that. And then R W x tilde, now is x tilde is available. So, covariance matrix for R W tilde will be given something like this. Carry out the expressions simplify that in between and things like that. We will be left out with this expression really. Now, what do you do with now P dot is by definition like this, okay, these two terms. So, you have one term and the same term transpose, and one term we need to derive. So, this one term is can be derived simply by definition, because x tilde dot we just derived here. So, we put it there, and x tilde is we keep it, then we proceed further like that way. And then e times expected value of x e times expected value of x tilde times x tilde transpose, this by definition is P matrix anyway. So, we will put P matrix here, then this one we just derived it the half times q z transpose, and then G is already there here. So, this is half times q z transpose. So, that will happen to be like that. So, P dot is this expression plus the same expression transpose. So, this expression what you have here plus the same expression transpose. Now, you simplify these two terms and half will be combined together, things like that. So, P dot happens to be like that basically, that is what I told here, P dot happens to be like that. So, what is the summary part of it again here? The model is given like this, okay, the continuous time model, the measurement is like this discrete time. We initialize the state vector as well as the covariance matrix, we compute the gain which is actually a discrete time manner, k is like this. And then once you compute the gain, you will be able to correct the state vector starting from the predicted value, we can get an updated value using this innovation term. Then we need to get ready with the next time step. Next time step we can propagate that way, the state equation can be propagated using this this part of the system dynamics, not including noise, and this covariance matrix can also be propagated that way actually. Okay, again this symmetric form is preferable. So, propagation sense we will make use of this propagation as I told, and we will also make use of this propagation term, and I mean this continuous time covariance matrix to propagate actually. Okay. All right. So, this is what I mean is this covariance matrix can also be updated there. Okay. That means, if you go back that, you are not only updating this state information here with the measurement, we will also update the covariance matrix here. Then we will propagate the covariance matrix using the continuous time expression that is available. Okay. So, this is update stage. Okay. Both the state vector as well as covariance matrix will be updated, then they will be propagated by one more time step actually. Remember, the way it is mechanized, it does not really require uniform delta t. That means, the propagation time step and updated time step need not be same actually. Okay. You keep on propagating as long as the sensor information is not available. The moment sensor information is available, you update the information that you have actually. So, that is a very neat way of mechanization actually. Also, I mean, this is what I already told, and then this is what it tells is like P dot expression is a continuous time Lyapunov equation. If you see this, is no more a Riccati equation basically. It's in a discrete, I mean, continuous discrete framework. It turns out to be nothing but a Lyapunov equation sort of thing. Okay. Now, finally, with this information, we will be able to touch upon this external Kalman filter, which is very popular in industry, and most of the time people use that external Kalman filter. So, facts to remember first is nonlinear estimation problems are considerably more difficult than the linear problems in general, and EKF turns out to be an idea, but not a cure for everything. That means that you just cannot tell that okay, because I know EKF, I'll be able to solve everything. But surprisingly it turns out that EKF actually works for a variety of problems actually. A large number of problems EKF does work, but in some cases it may not work also, okay, because EKF is not a very rigid precise theory, it's an extension idea really. So, what the problem is like if the nonlinear system, even if you take Gaussian input, it really does not translate, it does not retain Gaussian nature actually, okay. If it is a linear system, the nature of the Gaussian nature remains intact, but in nonlinear case does not actually. Okay. Okay. What is the assumption? Fundamental assumption. What you are assuming in external Kalman filter is that the true state is sufficiently close to the estimated state actually already. Okay. And in implementation it may not be actually, initially you will not be able to guess a very close state information and all that, and that is one of the difficulties of course, because universal stability like linear system theory is not available. Guess will play a role, and if your guess is too far away you will have a problem actually. But it turns out that you can have a fairly large amount of error in the initial guess, it will go through a large amount of transient, but it ultimately settles out nicely actually. Anyway, coming back, what it assumes that true state is sufficiently close to the estimated state, and hence we can actually linearize the nonlinear system about the estimated state, and then use linear theory that we have just discussed before actually. That is what the idea. So, let us talk about the most popular form, continuous discrete EKF, and that is the most natural form also. The system dynamics is continuous, but measurement is discrete again. So, what do you do here? Okay. So, similar idea, like we will be able to, like without the availability of measurement, we will be able to propagate the state information as well as the covariance information to the next time step, and as long as the system dynamics is available, we will be able to correct it actually. Okay. Sorry, as long as the measurement information is available, we can update this predicted values to corrected values really. So, that is the way it will proceed actually. Okay. Now, so what is the summary of this? The entire derivation will not go through probably, but the summary part is something like this. We have a system dynamics like this, where f of x u t u is this is the nonlinear system dynamics, remember that. Okay. But we still assume that the noise part is additive and noise part appears linearly based rather. Okay. And this output is again a nonlinear expression plus Vk. Okay. Remember the system dynamics is continuous, but measurement is actually discrete. So, probably you can put a k. Alright. So, again to mechanize this we need some initial condition, and then in that initial condition we have to guess, and so x hat k x hat minus t0 is x0, that is a guess, and p0 minus expected value of that, and that also a value of this matrix needs to be guessed. Most of the time these values are guessed as diagonal matrices anyway. Okay. And so, this is what is required. Then we will have a gain computation, okay, like fairly similar to what we discussed in the continuous discrete form of regular Kalman filter for linear systems. We will do that. But remember these are matrices now. So, matrices are actually this Ck minus what you are using here needs to be estimated this way actually. That means you take linearization of this output equation. So, Ck minus is linearized form of this equation actually. Okay. So, that is what will go here. And similarly, you will need I mean once you compute this Kalman gain, you will be able to use that for your update equations, and these expressions and all we have derived before. So, that is exactly same thing that you will be using. And then after we are done with this, we need to have a propagation thing, and propagation happens to be like that. So, we have a state equation which can be propagated without noise part of course, and then it is a covariance matrix I mean differential equation which will need to integrate actually. So, using that we will be able to propagate, and here this A matrix is again a Jacobian matrix which is derived del f by del x and which is evaluated about the current estimate x at t. Okay. So, A t and C t will be required here, C k minus and all that, and these are actually nothing but the linearization of the system dynamics and output equation what you have about the current estimate what you have actually. Okay. So, once you are ready with these matrices, you can treat that as at that point of time, that is my time varying system dynamics matrix that I have, and for that I already know how to deal with actually, because continuous discrete Kalman filter for linear systems is available to me. So, this is how you operate actually. So, every point of time you generate a and C matrices about something like a time varying linear matrix sort of thing, and then using your regular linear system Kalman filter theory, you will be able to compute the necessary matrices and all. So, okay, so again this operates based on this prediction correction like that actually. Okay. So, there is also an idea of this something called iterated EKF, that is the fundamental EKF anyway, but you will see that there are plenty of ideas of various extensions and then various arts and all, like how do you implement, what you do depends on your system dynamics, depends on your experience, depends on your insight to the problem, many things will happen around that actually. So, one of that happens to be this iterated EKF, where they tell okay, once I update these equations okay, here, let me again go back and tell okay, can I update one more time, okay, can I update one more time like that actually. Because the system matrix is this, we are talking about some sort of a linearization here, and linearization is about my predicted value. So, let me do the linearization again I mean with respect to the corrected value also, and operate the filtering equation one more time actually. So, that one you can keep on doing that, because you keep on updating your state and covariance matrix anyway. So, I will just update it and go back and tell okay, I will reevaluate this CK minus matrix about this x at k plus now, and then I will use that one actually now. Okay. So, you keep on updating several times before you proceed, I mean stop somewhere preferably after some convergence happens, and then you start your propagation equations actually, you start using your propagation equations. This is the whole idea of iterated EKF, and one can proceed with a fixed number of iterations, does not have to really wait for convergence and all. You can simply use some 2-3 iterations and all that before you proceed further. This is, remember, these are all like real time computation issues should be addressed also, because without that this has no meaning as also basically. So, we can use it based on fixed number of iterations, then go to the next step, like that actually. Alright. So, there are various recommendations and issues in EKF. So, before talking before stopping this lecture and winding up this course, let me talk several small recommendations that are given for successful implementation of EKF, and again I will talk in a very generic sense basically. So, first thing is the design choice and all that. So, design parameters, a lot of times you will see in the literature that these are the recommendations that will pop up. So, remember the tuning sense, what you really need is an initial condition guess for the state vector, and other than that we need values for these matrices R, P naught and Q, okay, right, P, Q and I mean what they call P naught, Q and R sort of thing, but you can think of that way. So, what they tell is like first thing is you fix your R matrix, because R is nothing but sensor covariance matrix. So, depending on what type of sensors that you have, that will be fixed from there, because you study the nature of your sensors and then find out the covariance matrix for that, and that is the reality. So, do not try to put out that too actually. So, keep your R matrix fixed based on the sensors that you are using. Okay. Then you select a P naught which is sufficiently high, that is a lot of times you will see that P naught value is recommended to be very high, and that actually helps in some sort of a stability behavior actually. That means, even though your initial condition guess is large enough, then also if your P naught selection is high, it turns out that the filter does converge after some initial transient of course. Now, once you fix R from the sensors and fix P naught sufficiently high, the only flexibility that you are left out with Q basically. So, you have to tune Q until you obtain satisfactory result basically. So, that is the standard recommendation that that is there in many literature actually. Second issue, if you see that, as I told, this EKF and all, it will go through initial large transients actually. So, initially it will go through large transients, and then ultimately it will try to settle, and after that the error will be small actually. So, obviously you do not want to use these transient values which are erroneous anyway. Okay. So, what you have to do is probably you should run the filter sufficiently ahead of time prior to its usage, so that the error stabilizes before its actual usage actually. Okay. So, if especially when you want to close in, that means you want to operate the estimated state into the control design and things like that. So, recommendation is you use the filter for you start operating your filter in the background for some time, and then after some time only you close the loop for the controller actually. So, that means by that time the error is stabilized, error is small, and then it will operate as if it is like a true estimated state and all that, true state and all. Okay. So, invariably you will see that there is some sort of a initial time lag given to the filter to stabilize before its actual usage actually. There is another recommendation I have seen many times, that lot of people are in favor of the idea that measurement equation is to be linear as much as possible. Okay. For example, the theory tells that okay, I can linearize the measurement equation as well and obtain a C matrix. But in general, what lot of practicing engineers who actually work in EKF have observed, that if you keep the measurement equation linear wherever possible, then it leads to better stability properties of the filter. That is just some sort of an experience recommendation sort of thing. There is no theory reasoning to back it up actually. Okay. So, one example is, for example, if you are talking about something like a missile guidance problem and your seeker or radar gets the information in polar coordinate, then the system dynamics associated with that you should also use in polar coordinate. Estimate the states in polar coordinate and then transform it to Cartesian coordinate if you need actually. But if you start with the Cartesian coordinate itself and use polar coordinate information as sensor output, then the measurement equation becomes nonlinear. Once you start linearizing it, you are truncating the information. So, these are some of the issues that you want to avoid actually. Okay. So, that is another recommendation. And appropriate care should be taken to avoid numerical ill conditioning actually, that you can see some of this recommendation in this Gratides-Jenkins book. This all of my discussion is from this book, and you can see that okay, one of the recommendation, as I told, is you need to use this expression for this pk plus instead of that simplified expression. If you use this will have better numerical properties, even though both these expressions are identical mathematically. Okay. So, that is another care that you need to take actually. Okay. One more big recommendation is we need to eliminate outliers actually. So, sometimes this sensor informations are not really good, and this EKF actually gives us a platform, because you have a predicted state, you have a measurement equation actually, which is like y and y hat sort of thing, and if the innovation term is really very big, then I do not want to account for that. Okay. If it is reasonably small and all, I will assume the sensor is correct, I will update. If it is too high, too big, then probably momentarily I need to ignore that. I will consider that some sort of a outlier and just ignore that actually. Also remember that EKF in general is fragile, that means the only a narrow band of design variables will be very good for successful operation. So, do not lose your patience, what I mean. So, keep on tuning this, and ultimately you will see that EKF actually works wonderfully for a number of problems, but you need to have patience for making it operational actually. And there are consistency checks of the Kalman filters. There are various checks actually. One is sigma bound test, normalized error square test, normalized mean square test, autocorrelation test, as like whiteness test and all that. There are Kramer inequality tests and all that. So, there are various tests available, and at least a few of them needs to be done to have confidence in your estimation and all that actually. That is certainly recommended, and you need to do that actually. Okay. There are limitations, linearization is not good, general convergence guarantee is not there, and blah blah blah, many issues. Because of that, there are other ideas available beyond EKF actually, and I will not discuss too many on that. If you are interested, you can see UKF, you can see particle filtering, you can see H infinity filtering, lot things actually. So, with that probably I will stop here, but then the reference books are available. The first book is my most favorite book, and that is what I have taken from. My second one is also good, and you can see some other books available. They are very good application book, there are theory books like that actually. So, with that I will stop here. Thanks a lot.